All right, so you should have 3 things. Let me know if you did not receive them. You should have bond, polarity, and whatever came after that to go in your red duotang. You should have a winter break gases package. And you should have the winter break gases package key. Is there anyone who needs any one of those 3 things who did not get one? Thank you. Do I have what?
Do you have another one of this?
Yes, I do. Yeah. I knew I'd missed somebody. I'm like, I have too many of these. There you go.
I mean, it's not annoying. It's nothing is nothing. She asked me, she asked me, how do you build a
All right. I would like you guys to tell your partner the name of the electronic geometry associated with 2 electron domains, 3 electron domains, 4, 5, and 6 electron domains. Bent is a molecular shape, not an electron domain shape. Two is only ever linear. It's never bent. Nope. Bent, we have to factor in lone pairs, and that'll be our molecular geometry as opposed to our electron geometry. Okay, and we're going to get to that today. All right, what's 2? What's 2? Linear. What's 3? Trigonal or trigonal, it doesn't matter. Trigonal, planar. Because it's like it's on a plane, right? And it would look like that, yes. And then we would have, what's 4? Tetrahedral. And if you needed to draw that, you would have one sticking straight up. You would have one going backwards, one coming sort of downish, and then one going forwards, and then it's always hard to draw these, right? I don't know. That actually isn't as bad as I thought it was going to be. Okay, I thought it was going to be a disaster. Now, what about 5? Trigonal bipyramidal. Two pyramids. Now, what does that shape look like? We've got our central atom. And then we have, which direction do things come out? One comes out the top. One goes out the bottom. What do we call those two? Those are axial. or axial, I don't know. Axial, axis, axial, sure. Yeah. And then where do the other three go? In a trigonal plane around the central atom, around the equator, like a tutu. Okay, so these are equatorial, equatorial, equatorial. That's where Ecuador got its name from, because it's really near the equator. Yeah. Okay, so that is our 5 electron domain. What is 8? What is 6 electron domain? Octahedral. And that one looks very much like the trigonal bipyramidal, except for, what's the difference? It has 4 around the equator instead. Excellent. Are we ready to throw in lone pairs? Sure. Okay, good. 11.4b. 11.4b, yes. I don't know. I don't know. We're just never going to do it. You guys will be here every day. You'll be like, oh, are we ever going to do that? No. Okay. All right. Okay. The effect of lone pairs. Some molecules have one or more lone pairs around the central atom. And that does not change the electron geometry. That's just part of the electron geometry. The lone pair can be one of those electron domains, right? They count towards the steric number. But the molecular geometry is specifically the arrangement of the atoms. When we are looking at the molecular geometry, we say, what does it look like if we ignore the 2 lone pairs, or the 3 lone pairs, or the 1 lone pair? Yes? No, it should be 11.5a. Yeah. Is it? What does it say? Oh, crumb. That's not what I want to say, but okay. Okay. Yeah. Yeah, no, the bond polarity should be 11.5a. Yes. When there are no lone pairs, the molecular geometry and electron geometry are the same. Okay, so here we have 4 electron domains with a lone pair. Now you could have no lone pair, and that would be like, if we had no lone pair, that would be like carbon tetrachloride or something like that. That's tetrahedral electron domain, electron geometry, and it is tetrahedral molecular geometry. But if we take NH3 and we draw its Lewis structure, it looks like that. Okay. And if you look at it with the lone pair, it is still tetrahedral. But if we ignore the lone pair, because if you're actually looking at, things that, are take up space and are, I don't know, actually real little balls in your ball and stick model, it doesn't look like a tetrahedron anymore, does it? It's missing that top of the tripod. So what we have here is we have a trigonal pyramid. But do we have 2 of them this time? No, we just have 1 of them. Okay, so we have this little pyramid back here. So this is trigonal pyramidal. Trigonal pyramidal. So the steric number is 4. But we only have 3 atoms. Or we can say the number of lone pairs is 1, which is normally how I think textbooks do it. They say the number of lone pairs is 1. So you need to know that if you take away the top of your tripod, what do you have? You have a triangular pyramid, trigonal pyramidal. Do you remember what happened when we had a double bond somewhere? What did the double bond do that was different from a single bond? It pushed more. Turns out lone pairs are also more repulsive. Yes, lone pairs are more repulsive. So it's going to look a little bit more like a pyramid. So what's going to happen is instead of being like this, it's going to be like this. Like everything sort of gets a little squished together. Yeah? I'm not very good at making my fingers straight. This one wants to like go out to the side there. Okay. Is it what? Instead of in a line, yeah, exactly. So like a little 3-prong thing. Very much like a plug for an outlet, except for that things are kind of on the diagonal. They're on angles. Oh, so lone pairs usually exert more repulsion than bonding pairs because they are more spread out in space. At least that's what it says here. I'm willing to go with that. It sounds good to me. Okay, you're not going to have to explain why. You can just be like, okay, lone pairs are more repulsive. They compress the bond angles. So instead of 109.5, what are you going to say? Less than 109.5, because you do not need to memorize that, you know, it's 107 for ammonia and 10 whatever for whatever. Okay, just less than 109.5 is a happy way to do it. Oh, and look, I've said that here. Isn't that nice? Okay. Four groups with 2 lone pairs. This is water, and this is where we get into our bent structure. But you'll notice this bent structure doesn't have just 2 electron domains. How many electron domains does it have? 4. Okay. So we have our tetrahedron. We have 2 lone pairs. So all we're looking at is this molecule, which is bent. What is that bond angle going to be? Less than 109.5. And if we were to compare it with ammonia, right, which one would you expect to be smaller, water's bond angle or ammonia's bond angle? Water, because it's got 2 lone pairs repelling, okay? You might even say less than 109.5, but I'm not going to do that because it's going to be too complicated and confusing, okay? So this will be smaller than the angle in ammonia. Because, which I don't have room to write, so I'm going to write because there's more lone pairs. Therefore, more repulsion. And if you're into that kind of thing, you can notice that it's 104.5. They all sound like radio stations. 109.5, 104.5, 103.5, QMFM. Is it? I listen to CBC FM, I listen to Jack, and I listen to whatever the one is out of Bellingham that does classic rock. No. I'm old. I like the 70s, 80s. What's that? I love cross country checkup. Yes. Oh, okay. Anyway, it's okay. I was off there too. Okay, so the repulsive, relative repulsion, lone is more than lone, bonding is more than bonding. Okay? There's the comparison. So all three of these have tetrahedral what? Electron geometry. But they all have different molecular geometry. Is good? Okay. Oh, I wrote that in the, I don't know why I write anything on these. I've already written it. I'm like, oh, that sounds good to write. Okay. Now we come to my very, 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 very favorite shape. So we have here 5 electron groups. And in this case, we have SF4, and you'll notice the Lewis structure for SF4 has 4 bonds, and it has a lone pair. So what's its electron domain shape? Electron geometry is trigonal bipyramidal. Okay. But, and this is the one where it's a little bit tricky because you have to remember where the lone pair goes. Lone pairs always go around the axis. Equator. Sorry, I'm like axis. They always go around the equator. Okay? It's because there is less repulsion there because we have 120-degree bond angles between those ones, whereas this one has a 90 and a 90 and a 90. Okay? So it is better for the lone pair because it is more repulsive to go in that sort of middle section. Okay? Now, because this happens, the geometry is called, okay, I don't like this name. You could also call it a distorted tetrahedron, but that makes me sad because you could call it a seesaw, because if you turn it sideways, you can have a little person sitting there, right? And a little person sitting there. Okay, I don't know. They seem to have like disemboweled themselves on the thing, but anyway, there we go. Right? And they go up and they go down. And in fact, if you make the molecular model, you can make it go side to side. You can be like, oh, little seesaw. Now, what do you notice about this angle between the axial and the axial? It's not 180, it is slightly less than 180. Yes. No, no. Like what you might be asked to do is to draw the Lewis structure and then determine the molecular geometry. Okay. So if there is one lone pair missing, it becomes a seesaw shape. Seesaw. And here's another good shape. I like these names, right? They're not like weird pyramidal bi tetra thing. Okay, this one is T-shaped because it's shaped like a T. So once again, where do we replace, where do the lone pairs go? Do they go axial or do they go equatorial? Equatorial, okay? So once you put a couple on there, you now have T-shaped. This will be somewhat less than 90 degrees, and this will be somewhat less than 90 degrees. Now what if we have three lone pairs? They all go equatorial, and what we end up with is, guess what? Linear. Yep. So you can have 2 electron domains and be linear. You can have 5 electron domains and be linear. Here are all the shapes for the 5 electron groups. Trigonal bipyramidal, seesaw, T-shaped, and linear. All of the electron domain shapes are trigonal bipyramidal. And we're not quite done because we still have to build on our octahedral base. So we have, that's a lot of candy. That's a lot, those are big candy. Okay. Now, does it matter whether the lone pair removed is axial or equatorial? Does it matter? No, because everything's at 90 degrees, right? So, I mean, you could turn the molecule sideways and all of a sudden the things that were equatorial are now axial, right? It's not like the other one where you've got 120 degrees. These are all 90 degrees. So it doesn't matter where you put it. So we may as well put it on the bottom so that when we look at this, we could actually see our square pyramid. Yes? Because every single bond angle here is 90 degrees, right? Whereas the other one, we have to put these in where we have the 120 in between because they're more repulsive. And so they would prefer to be where they can be further away at 120 degrees away from another lone pair or another set of electrons. Whereas this one, it's like, if I put it here, it's at 90 degrees. If I put it here, it's at 90 degrees. If I put it here, it's at 90 degrees. It just doesn't matter because they're all the same bond angle, okay? So this is square pyramidal. Square pyramidal. Can you guess what happens if we take away that top F? Like if we were to get rid of that one. Square planar. Because it's a square and it's in a plane. Oh, hang on. This is what we get. Yes? And these ones are going to be exactly 90 degrees because there's no, like they're being pushed down more, but they're being pushed up more. And so it all cancels each other out. Yes? So here are all the shapes For 6 electron groups, we don't get more than 2 lone pairs. So there's less shapes actually than for the 5 groups. So we have octahedral, we have square pyramidal, and then we have square planar. The geometry of the molecule is determined by the number of electron groups. The number of electron groups is determined from the Lewis structure. So if you want to do this, you need to be able to draw Lewis structures. And the geometry of the electron groups is determined by their repulsions. And so multiple bonds repel more, lone pairs repel more because they're bulkier. Lone pairs are more repulsive. And there we go. Is good? Okay. Predicting the molecular geometries. We're going to do a few little practice here. Okay. So we are going to predict the molecular geometry for ClNO. Nitrogen and oxygen, or sorry, nitrogen and chlorine actually have the same electronegativity, so we can choose to put whichever one we want in the middle. I'm going to put nitrogen in the middle because it's not a halogen and it has a tendency to form more bonds. Okay. So I'm going to put my nitrogen in the middle. I'm going to put my oxygen here, my chlorine here. What have we drawn now? We have drawn our linear, except for we're not done yet, right? I've just drawn the skeleton structure. Okay. Now, what do we need to do to complete this Lewis structure? We need to find the valence electrons. Chlorine has 7, nitrogen has 5, and oxygen has 6. Now, I have to say, I have not marked your tests, but when I was walking around, I was not like as happy as I might have been with where people were kind of going with some of their Lewis structures. So, and it's because we went through it very quickly. You know what I mean? When I did it with the regular 11s, I held their hand a lot, right? And you guys did not get your hand held nearly as much. So we're going to do a little hand holding here. Yes? Because we want to improve on our Lewis structure skills. For example, I did see several structures that did not have a complete octet. Right? There was like a carbon and it had 6 electrons and I was like, ooh. Right? And that just means you haven't had time to process it yet, right? So we have 7 plus 5 is 12 plus 6 is 18. What's the next step? Draw in all the lone pairs, every single one of them, everywhere. Okay. Now we're going to do what? We're going to count them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Uh-oh. So I have too many. So I have to erase. How many do I have too many? I have 2 electrons too many, so that's 1 pair too many. So we're going to erase 1 pair from the central atom. When we have 1 pair too many and we erase 1 pair from the central atom, what we need to do is we need to take 1 lone pair and turn it into 1 multiple bond. So if I erase this here, take 1 lone pair and turn it into 1 multiple bond. So this is going to tell me how many multiple bonds I'll need. So when you had the structure, did I give you carbon monoxide, I think? Carbon monoxide, you had to erase 2 lone pairs. And so you would have to form 2 multiple bonds, which would give you a triple bond. Yes? Did you guys catch that? No. A lot of you did do it, but I did notice there were a few people who didn't. Okay. So if you have carbon monoxide, you had to erase 2 lone pairs. Okay. And so you would have to take 1 lone pair and turn it into a double bond, and a second lone pair and turn it into a triple bond.
I was right.
But that's how you know how many double or triple bonds or whatever. That's why I say multiple bonds, because if you have 2 multiple bonds, that could be a double bond and a double bond, or it could be a triple bond, like 1 triple bond. Okay? So let us take 1 lone pair. Who should I take it from? Should I take it from chlorine or from oxygen? How many bonds does chlorine like to form? How many bonds does oxygen like to form? Let's take it from oxygen, shall we? It's also going to work out much better in terms of the formal charge. Why does it like to form 2? Because it's got 2 holes in its outer shell. Yes. Yes. So if we look, I'll draw the 2 structures and give you the formal charges, okay? Now, let's take a look at this, okay? I'm also going to draw the alternate structure. This is a good one. This is a happy structure. This is a much less happy structure. It's not that it is impossible, it's just that it is not as lovely. I think you guys have gotten very, very excited about having resonance structures that are not equivalent. Yes? We're all like, non-equivalent resonance structures. These are non-equivalent, right? Because they don't have the same formal charges. If you had, say, nitrate, on the other hand, the nitrate ion, you would have equivalent resonance structures because it doesn't matter which O, right? They're all equivalent. So these are all equivalent resonance structures. So formal charge will, on all of the oxygens, will be identical. Because the double bond's on oxygen every single time. What you really have is you have that bond really isn't here or here or here. It's really in all 3 places, all at the same time. Yes? No. It would spend some portion of its time over here, but not nearly as much, and so we don't know. So I would say Ignore resonance structures like this unless they specifically ask you for them on the exam. Yes? Unless they're like, oh, please draw me a resonance structure of this thing, that thing. Then you could be like, okay, I could, if I wanted to, if I had to, move that bond. But this is not a situation where I would go out of my way to draw a resonance structure. Whereas this is incorrect if you don't draw a resonance structure. Yes? I suppose you could, but that's taking you time, and you don't have time, yeah? And I mean, I've been looking at what they want from you for Lewis structures. They usually provide you with the skeleton and just let you fill in the lines and the dots, right? They give you a box and there's like stuff and they have you write the lines and the dots. So don't get so excited about all the exceptions and the weird things and because they don't want the exceptions and the weird things and the whatever. They just want you to be able to draw normal Lewis structures, okay? So here we are, this is our structure. Now, where were we going with this? Oh, we wanted to predict the molecular geometry and bond angle. So when you are predicting the geometry, you need to look at the, which atom? The one in the middle. So you're looking at this one, and you're saying, how many electron domains? 3 electron domains. How many lone pairs? 1 lone pair. So what we're going to have is we are going to have, what's the main shape? What's the electron domain shape? Yeah. Is trigonal planar. And the molecular shape is, and this is how we draw a lone pair. We sort of draw a little balloon representing the area where we would have that. So that would be what shape? Bent, right? Because we've got that bit. What's the bond angle going to be there? Less than less than 120, because that's a third and a third and a third. Normally, trigonal planar would be 120, but we have now less than 120. And this is why I've assigned you gases over Christmas rather than molecular shapes, because molecular shapes are a little bit like, woo, whereas the gases, they kind of make sense. And it's all just like multiply and divide. It's like P1V1 equals P2V2. I give you 3 of them, solve for the 4th. Whoa. You don't need to know. If I gave you, and if I said P1 is this, V1 is this, P2 is this, solve for V2, would you be able to do it? Bam, that's what you're doing over Christmas. Lovely, right? Predict the molecular geometry of I3. I. Oh, that's too many. Canta, no llores. What do I need to do next? Count the valence electrons. I is, we have 3 times 7 is 21, but it is also negative. So we have 22 valence electrons. Dun 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 dun. All right. How many do we have now? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 20. So that is one pair too many, yes? Oh no, it's one pair too little. One pair too few. Oh, that's different. What do I do when I have one pair too few? I just add to the middle, so I'm going to chuck another pair on there. Okay, we just threw those extra ones on the middle. Do we need to do anything with bonding, double bonding? No, because you only do that when you don't have enough electrons, and we had too few electrons. Now that we have our Lewis structure, look at your central atom. How many electron domains? That's 5. Steric number is 5. Therefore, the electron geometry is trigonal bipyramidal. Okay, so that's nice. We have 1, and we have axial, axial, or axial, axial, equatorial, equatorial, equatorial. That's our electron domain shape. But we are going to replace how many of those with lone pairs? 3 of them with lone pairs. That's a sad little drawing. That one looked like a newt. So this is now going to be linear. Yes. Yes, there will be a bonding test after winter break, but I'll give you some review when you come back. I want you to just, I don't want to have you do too many things over the break, so just do the gases stuff over the break. We'll come back and we'll do a review on this and finish off anything we haven't finished. Now, you might be called upon to predict the shape of a larger molecule. Okay, why is there this like square in the middle of things? I'm sorry, there's a square. It must have been I was doing something and forgot to erase it. Okay. Oh, I know why, because it's supposed to be a white square and it's supposed to go over this little bit here, but it never made it white and it never made it to where it was supposed to be. This. Okay. So we now have this great big molecule. It's not that big. It's called glycine. But instead of having one central molecule, or sorry, one central atom, we actually have 4 different atoms in the middle. Yes? Now, the nice thing is that none of them have like 5 electron domains or 6 electron domains. So we're dealing with nice things that are either based on trigonal planar or they're based on tetrahedral. And most of those you'll be more familiar with as we go through, okay? So if we look at the N, What's its steric number? Steric number of nitrogen? 4. How many lone pairs? And when we have a tetrahedral shape, but one of them is a lone pair, what are we left with? Trigonal, we're left with a triangle pyramid, so trigonal pyramidal. And if we look over here, you can almost see it. I mean, it's not beautiful because, you know, we can't, this hydrogen here is sort of, you know, sticking out here, but you can imagine it's coming out towards you. And then these two are like this. So we have a little pyramid with three points. Yes, but it's kind of like this. Yeah? Now, we have a carbon here. This carbon here, what is its steric number? Steric number equals 4. Lone pairs equal 0. Therefore, it's sp3, and what's its shape? Tetrahedral. How about this carbon? Steric number is 3. Any lone pairs? Lone pairs is 0. Therefore, what's the shape? Trigonal planar. What about oxygen? Steric number is 4. Lone pairs is 2. Therefore, it is bent. And mostly if you have larger molecules, you're not going to have things with like 5 domains and 6 domains. They're all going to be like, you know, 3 and 4. Okay. Maybe 2 at the most. All right. So that's how you would do it. We already had this page, didn't we? Like this picture? Did we? But if we didn't, I thought it was worthwhile, because even though I don't think you need to do this for the AP exam, if you're going to take any sort of chemistry, especially organic, it'll become really important. Straight line means the bond is in the plane of the paper. A hatched wedge, which is where you have like little dash, dashity, dash, 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 dash getting bigger, which I can't really draw because that would require me to have some control over my pen. But that's going into the page backwards, and a solid wedge comes out of the page. So you can see the shapes are here. Very nice. Okay. Could you predict the geometry around each interior atom in acetic acid? So first of all, you have to determine who are the interior atoms. So who are the 3? C, the ones in the middle, C and O. No, I just had blue. There we go. Okay. Carbon, steric number. Yes. They matter in that they repel more, and so they make the bond angles somewhat less than whatever. Nope. Nope. Yep. Yep. What's the steric number of that carbon? 4. Because we have 1 where we can see the bond, and then we got 3 other hydrogens. What's the molecular shape? Molecular geometry is tetrahedral. Steric number 3. Molecular geometry. Trigonal planar. Oh, now here's a nasty one. What's the steric number on this O? Ooh. 4. Because you have to remember that sometimes when they give you a structure, they won't draw in the lone pairs. So you would need to have drawn those in for yourself so you don't remember, or don't forget, so you don't forget. That's what I meant to say. So we have a steric number, which is 4, and that means that we have 2 lone pairs. Therefore, the shape is bent. Is this seeming manageable? Yes? I mean, a few of the names need a little practice and whatnot, so yeah. But other than that is good? Okay, cool. Well, if you wanted to draw the diagram, you could be like, okay, I got a carbon, and I've got 1, and then 2, and then 3. What direction should I put the line going to the oxygen? Going slightly down because I've got my trigonal pyramidal, or not trigonal planar shape there. So now I've got the oxygen, and then this one is bent, so you could just be like H, put it bent wherever, you know. Is good? Okay. Awesome possum. Shall we?
has little kids. Yeah. Even though you don't feel it watching it. No, they just expect you to be good at reading.
Excellent. And if I teach anything tomorrow, it'll be recorded and online. Yeah.